All right, what's up, all of my stat stars out there? Hopefully you could hear and see me okay. This is my first ever live review session, so if something goes wrong or if I mess something up, please don't get mad at me. Also, I'm going to be looking down a lot because I'm going to be trying to read you guys' comments. I've already saw a ton of comments. I got a lot to talk about. But if you could avoid trying to put comments and don't ask questions because it just muddies the water for me to kind of look through things. And if all goes well, if this goes well and everybody likes this, we get a lot out of it. I plan to do another one Tuesday morning before the exam. I'm not 100% sure on the time yet, but if I do all that, I'll get it scheduled so you guys should see it up on my YouTube channel. But hopefully everybody's doing okay out there. And I'd like to just jump right into answering some of the biggest questions that people have. But before, I want to mention two things. Those that are looking for more studying, please check out my ultimate review packet. It is awesome. If you haven't seen it already, I'm sure a lot of you maybe already have, but my ultimate review packet could be purchased on ultimatereviewpacket.com. It's got tons of practice questions. It's got study guides for every single unit. It literally has everything you'll need to prepare. So if you are looking for that last major push, last major practice to get ready for the exam, you'll find tons of stuff there. Also, a lot of people are asking questions for a lot of topics that I have videos on. And listen, I would love to sit here all night and talk to you guys and answer some questions, but I already have tons of videos that answer all of your questions. So if you go to my YouTube channel, right kind of in the middle, there's a bunch of little tabs. And next to all those tabs, you'll see a little magnifying glass. If you just type in anything you're looking for, t-interval, t-test, two-sample t-interval, confidence intervals, whatever it is you're looking for, I'm sure I have a video that explains it all in way more detail than I can give you right now. So please don't be afraid to take a look at that. And hopefully if I don't get something that you have, a question that you have, I don't get it answered right now, hopefully there's a video that you can watch and I'll try to get through as much as I can. All right, so just kind of starting off with a couple of things. One person asked here, can you please go over a mean difference and how to interpret the p-value for it? This is probably the top most popular question I get, not only from my own students, but from kids on YouTube, is how do you do this matched pair t-test? So a couple of most important things with a matched pairs t-test. First, it is performed exactly like a regular one sample t-test when you're working for means. The difference is how the problem is presented. So a matched pairs test, it might look like you have two sets of data, but there's really only one sample. So this is a great example of this is an experiment where you have matched pairs experiment where you have one group of people that get measured twice. Maybe you measure people before and you measure people after or something like that. There's been problems in the past on AP exams. One was something where they were testing meat for E. coli and they had 10 meat samples and they tested them with two different devices. But again, there was one sample that got tested twice, thermometer 1, thermometer 2, or whatever the problem was. So in this problem, the most important thing that you know is that you don't need each sample. What you need is the differences between the two. So I'm actually going to pull up an example real quick here so we can see this and you can understand exactly kind of what I'm talking about. And we'll go from there. So let me pull it up here. Just give me a minute. We have 8 different screens going on here. All right. So here's the question I'm talking about. Makers of a new skincare healing ointment want to determine if their new ointment heals wounds faster than nothing at all. 8 volunteers are used in the study. Each volunteer is given a similar cut on each of their forearms, left and right. Sounds pretty unethical there, but we'll still run with it. And what they decide to do for each subject, they will randomly determine which arm gets the new ointment and which gets nothing. Now, so the key thing here is there's one group of people and they have 2 arms. Their arms are matched together and each arm is going to get something. One gets the new ointment, one gets the old ointment. Give me 1 second. I'm trying to figure out how to turn this comment off here and see a little bit better. I'm sorry. There we go. Okay, so on the next page of the data from the experiment, is there significant evidence that the mean time to heal a cut is shorter than the new ointment than the no ointment at all? Now, here's the deal. Typically, this is going to come up in a multiple choice question. Like they give you a scenario like this and they ask, what type of test is going to be needed, and they might even show you the data. And, you might see something that looks like this. You'll say, oh, there's 2 sets of data. I see two columns of data. But we got to remember there's only one group of subjects. And what we care about is the difference, because these two people were clearly paired together. They had two different arms. Each arm got a cut, and one had the old cut, or one had the new ointment, one had the no ointment. You get the idea. But this is where you definitely want to match together, that this is a match pairs t-test. So real quick, what you care about most with a problem like this is the differences. What you want to go through is actually get a list of differences. So 3 minus 5 is -2, meaning the ointment heal time was 2 days faster. For subject 2, 4 minus 7 is -3. So again, 3 days faster. Now, what you then want to do is go to your calculator. And then honestly, in some problems, they already have it all done for you, where they already have a third column of the differences. Like, that's another easy sign that you're working with a matched pairs t-test, is you'll see a third column that is filled with just the differences. So what you want to do is go to your calculator to get these values. I'm actually going to pull my calculator up here real quick so you can see. So you're going to go to Stat, Edit, and I actually already went ahead in there and I put in all of the differences. So, -2, -3, 0 for subject 3 who had no difference. And then I'm going to do a stats, slide over to calculate, one variable statistics here, and I get the mean. So that means the top is the mean difference. So on average, there was 2.75 days healing faster on the new ointment. And then I also need that standard deviation right there, 1.488. Now, here is what my null would look like. My null hypothesis would be that the mean difference is 0. We would assume that there's no difference. The new ointment, no ointment, doesn't even matter. And the alternative would be that there is, in fact, a difference less than 0. Now, another question a lot of kids ask is, what if I subtracted in the other order and I had a positive 2.75? Doesn't matter at all. You would therefore have an alternative that the mean difference is greater than 0. You just have to understand that. But the most important thing, like I tell kids all the time, the most important thing about a test is that you name it. This is a one sample paired t-test for the mean difference. And then don't forget the context, the mean difference of what between the time for a wound to heal with the new ointment and the time to heal with no ointment at all. Now, then we're going to actually go ahead and get that t-score and that p-value. Now, here's like my actual work for how I got that. So I took the -2.75. That was my observed mean. I subtracted 0, and I divided by the standard error. So let me show you how I got that standard error real quick. The formula for standard error is taking the standard deviation of your sample. In this case, that was the 1.488, and dividing it by the square root of your sample size. In fact, I think I actually have that work shown right here. Yep, there it is. The 1.4880 divided by the square root of 8, my sample size, and that's how I got the 0.5261. Now, for those that are wondering, because it's another very common question, is why am I not using a z-test here? Anytime you're working with means, and the problem deals with an interval for a population mean or a test for a population mean, even this problem where it's the mean difference, and the only standard deviation you know is the standard deviation of your sample, that's when you're going to go and use t. If you did know the population standard deviation, you could do a z-test. But I'm going to tell you right now, in AP statistics, that's never going to be the case. For intervals or tests with means, we're always using the standard deviation of our sample, which means we need a t-test or t-interval. All right, so then I got that t-score, and then I used a t-CDF to find the probability that any other mean difference is less than mine, and that's how I got my t-value. Now, I do want to emphasize that your calculator could do all that work for you, because it's another thing is I have a bunch of videos that show all the different things your calculator could do for you. So I would hit Stat, I'd slide over to Test, and this would be a t-test. Now, again, I know this is a test, a match pairs test for means, but I'm still going to treat it, the calculator doesn't know the difference, but I'm still going to treat this as a regular t-test. But I know that it was a match pairs t-test for the means. So the first thing is I need the null hypothesis. That would be 0. We assume there was no difference. Now, if you actually have the data entered into your calculator, I could select data, and I actually do have the data entered in my calculator, so I would use list 1. But you could also slide over to stats up at the top here, and then this is where you would put in your actual mean, the -2.75, and the standard deviation as well, and your sample size. Either way, you're going to get the same values, whether you use the data in the calculator or you type it in. And then you want to make sure we choose the proper alternative. We were specifically looking for the mean difference to be less than our null of 0, because we were trying to show that the new ointment heals faster. That's why I got those negative values. And hit calculate, and boom, there's the t-score, -5.227, and then my p-value of 0.00060, whatever. But again, pay attention. Don't forget about on that p-value, that e to the -4 tells you to move the decimal 4 places to the left. Now, with a p-value that low, of course, I'm going to reject the null. And that's why I said I will reject the null. There is significant evidence that the mean difference in time for a wound to heal with the new ointment is less than 0. And I do have evidence the new ointment heals wounds faster. Now, hopefully that made sense. But again, matched pairs tests actually are pretty common on the AP exam. If they're not always going to be on the FRQs, but if they are not on the FRQ, there's definitely going to be a multiple choice that talks about it, as I already mentioned. But a lot of kids were also asking in the chat about using the calculator. When do I have to like write down everything that I type into the calculator? The answer to that is no, right? We do not like to see what we call calculator speak. We don't want you to write down normal CDF or invert norm or TCDF, or I did a t-test on my calculator and here's what I typed in. We don't want that. The most important thing that you start off with is naming the test or the interval. Name what you're doing, whether it be a one sample Z test for a population proportion, or a one sample T test for a population mean, or a matched pairs T test for the difference between this and that. But it's super important that you name the procedure. That is so important. And then getting those hypotheses correct, checking those conditions. And then if you do use your calculator to get your test statistic and your p-value, that's totally fine. You don't have to write down, I used my calculator, but it's really important that you name the test. Then you could say, oh, my t-score was this, my p-value was this, and then here's my conclusion based on that p-value. We really value naming the test, the proper conclusion, and then if you did use the calculator to get your p-value and your t-score, totally fine. So hopefully that clears that up. A lot of questions there about what I have to show from the calculator and whatnot. Next question a lot of people asked about was question 6. Question 6 is a tough one. Sorry. I tell my students there's nothing, zero I could do to prepare you for question 6 other than just teach you the entire year as I did. And then hopefully you will be ready for question 6 just based on your own knowledge. But don't be afraid of question 6. It's actually not always that bad. In more recent years, it's been way easier than it's been in the past. And oftentimes, maybe the third or fourth part is difficult, but part A and part B are usually really, really simple. They're not overly difficult. They're something that you already know very, very well. So the big thing that I also want to make sure I tell you guys, I said this in a couple of my videos, you are given 90 minutes for all 6 free response questions. It says on the test to spend 65 minutes on part A, which is questions 1 through 5, and spend 25 minutes on part B, which is question 6. But your proctor is not going to set a timer and say, hey, 65 minutes is up. It's now time to work on part B. That's not going to happen. You can work on them in any order. You could start with number 6 if you want. You have 90 minutes for all of it. The 65 and the 25 minutes is literally just a recommendation. So I tell my students, do everything you can to get 1, 2, 3, 4, and 5 correct. 1 and 2 are usually very easy. They deal with exploring data and collecting data. They're not that difficult. Then try 3, 4, 5. Make sure you answer every question. Then if you look at the clock and you have 10 minutes left, spend 10 minutes reading number 6. Maybe you can get A and part B correct, or at least attempt them. If you look at the clock and you have 30 seconds left, oh, well. I mean, it's not the end of the world. As I've mentioned in a lot of videos, you could score really well in the exam, and you don't even have to get any points from question number 6. All right. If you did roughly half the multiple choice correct and half credit on all of the FRQs and a 0 on 6, you're still going to get a passing score of a 3. All right. So more questions that come up. Another one people asked about was the different types of chi-square tests. So there are 3 different types of chi-square tests. Goodness of fit is the easiest one to recognize because there's only one categorical variable. There might be multiple categories like brown eyes, blue eyes, red eyes, hazel eyes, amber eyes, whatever, but there's only one categorical variable. And what you're trying to see is how well does it fit? How well does the observed data fit with what we expect? Now, how do you know what to expect? You simply have to read the problem. Maybe it says that they were expected to all be equal. That means they're all supposed to be the same value. Or maybe they give you some historical proportions or percentages that each one is supposed to be based on. But a goodness of fit test is simple to recognize because there's only one categorical variable. Now, a test for homogeneity or a test for independence has a 2-way table. So there's going to be 2 categorical variables, one on the left of the table, one on the top of the table. Now, how do you know which test it is? Well, you got to read the problem. Now, the good news is how you approach the test is actually the same, whether it's homogeneity or independence. But you do need to name it. As I already mentioned, naming the test appropriately is worth a lot of points and very important. So a test for independence is when you're looking for an association. So you have one sample that you ask two questions to. I did an example where we had a group of people and we said, are you male, female, and what political party are you? And we were looking to see if there's a relationship between gender and political party. But again, it was very clear in the directions that there was one sample. We simply asked them two different questions. Other questions I've seen in the past were looking at college students, one sample, we asked their gender and we asked how much they work. Do they have part-time job, full-time job, part-time job in the summer, not in the summer, all those kinds of questions. But again, one sample and we're looking for an association. That's how you're going to recognize a chi-squared test for independence. Your null would be that there's no association, and the alternative would be that there is an association between the two variables. Now, a homogeneity test, there are clear evidence of more than one sample. So maybe you have three different samples, 9th graders, 10th graders, and 11th graders, and then you're looking at another variable across them. So again, the problem will be very clear in saying we did three random samples, one of 9th graders, one of 10th graders, one of 11th graders, and then we're trying to see if the distribution of that second variable is the same across those different samples or those different populations. So if you see those signs of more than one sample, that's going to be leaning towards a homogeneity test. And then again, you also got to read the question. The question saying, is there an association? It's going to be a test for independence. And if a question says, hey, is the distribution the same or is it different? That's going to be a homogeneity test. And again, your null would be everything's the same. The distribution is the same across the different groups. And the alternative would be that there's a difference. All right. Somebody asked about linear regression conditions. I tell my students, don't even worry about it. Obviously, I could shoot myself in the foot, and this is the year that there's a big question about linear regression conditions, but I highly, highly doubt it. There are just too many of them. There's a lot of conditions, and some of them are very confusing. So what I tell students is I'm almost going to promise you won't have to deal with them, but if you do, they'll say in the problem that the conditions have all been checked. Typically, there is always a multiple choice question where you're going to construct a confidence interval for the slope of a regression line, and you're going to be given one of those computer output tables, and literally everything you need is in that table, and it's multiple choice. You don't have to check the conditions at all. Now, I think last year or maybe the year before, I think it was maybe number 6, I can't remember for sure, but there was an FRQ question that did ask about linear regression, asked about slope, but you didn't have to do the whole problem. And first off, it was like the 4th part of the problem. So even if you got everything else right before, you could still probably get 2 or 3 points in that question. But again, going back to that question, they simply were saying, hey, what are the hypotheses, or can you interpret the p-value? What conclusion would you give? And you should know how to do that. But again, checking the conditions for linear regression just don't ever come up. So just don't worry about it, would be my honest opinion. A lot of kids, somebody asked also about using the calculator. I think I already mentioned that. Never use calculator speak on the exam. But if you are going to use invert T or invert norm. So let me pull this up real quick. I want to make sure I show you guys this. I hope everybody knows how to use their TI-84 calculator. And somebody always asks me, oh, what about a Casio calculator? I'm really sorry. I don't know how to use the Casio calculators. So I apologize. But let me just show this real quick here. So when you go, if you have one of the newer calculators, when you do an inverse norm, now what inverse norm does is it gives you the z-score with a particular area typed in. Now, the newer calculators, you could select left, center, right. So if you're looking for, the z-score that has 20% at the bottom, that'd be 20% to the left, you type in 0.2 and you'd select left. Or if a question says, what about the 20% at the top? Well, then you type in 20% and you'd select right. Or if it's talking about 95% in the middle, well, then you could type in 0.95 and select center. But the older calculators don't have that feature to select the tail. So it was just defaulted to left. So for people that have those older calculators, if it talked about the top 20%, you would have to type in 0.8. And again, simple math in your head, right? There's 20% at the top. That means there's 80% at the bottom. So those older calculators are always defaulting to the left. The newer calculators, you actually have the option. Now, I'm old school. The calculator I had back in the day only did towards the left and only did the bottom. So like I always just leave mine on left. And if they're talking about the middle 95%, well, then I think about the bottom 2.5%, and that's what I would type in. But when you go to use invert t, let's exit out of here. When you go to use invert t, well, all kinds of wrong buttons here. Invert t, even on the new calculators, doesn't have the option for left, center, and right. It only does left. So when you do invert t to get a t star or a critical value for t star, notice how there's no option there for left, center, right. So if I'm looking for, so let's say the t star for 95% confidence interval, I'm going to type in 0.025 because if I'm 95% in the middle, that means there's 5% left out, 2.5 at the bottom, 2.5 at the top. And then don't forget the degrees of freedom, which is simply your sample size minus 1. So let's say I have a sample size of 10, of 9 degrees of freedom. And I'm going to go ahead and hit paste, and I'll get my t star here. Now, if you don't have a T94 calculator or no one ever taught you how to use invert t for that, somebody also in the chat asked about using the t tables. Now, let me just quickly show you those t tables here. This is really old school, but here's one of those t tables. And basically what you would do is across the top of the table, it says tail probability. So again, for 95% confident, the tail probability would be 0.025, 95 in the middle, 5% left out, 2 at half the top, 2 at the bottom. So you would find that column for the tail probability, and then the left-hand side is your degrees of freedom. So as the problem I just did had 9 degrees of freedom, so I'm going to just track over 9 degrees of freedom with the tail probability of 0.025 would be a t star of 2.262 there. So you just got to look it up. But again, if you have a T94 calculator, there's really no reason for you to ever use these t tables because we have the calculator to do all that work for us. So hopefully that makes sense from that. But if you don't have to write on your test, oh, I used invert t. You just get the right t star for that particular problem. Okay, so I answered a lot of questions there. Let me kind of go back here. One more question somebody asked was about margin of error. They kind of said, can you explain what margin of error is? So margin of error is basically saying, hey, we have a sample statistic, whether it be p hat or x bar, but that's just a sample. And the one thing samples do very, very well is that they vary. So, I'm going to subtract that margin of error. Now, the margin of error formula is on the AP Stats formula sheet, but it's very generic. What they listed as is simply the critical value times your standard error. So multiply them together, you get your margin of error. Now, the critical value is going to be either a z star or a t star. Now, if your problem deals with proportions, you're trying to find a confidence interval for a population proportion, trust me, you're always using a z star. You're going to use invert norm, or you're going to use your z table to figure out what that value is. Now, and then for standard error, you have to go ahead and use the formula sheets, right? Look up the formula for standard error for proportions, whether it be one proportion or two proportions. There's those two formulas are on the formula sheet. Multiply that together and you'll get your margin of error. Now, if you're working with means, then your critical value is your t star, and they're going to multiply that by your standard error. And once again, go to that formula sheet, look up. Actually, let me show you that real quick. It could be worth me just showing you this so everybody hears, because that formula sheet is really valuable when it comes to getting that. All right, here we go. All right, so there it is. So again, if I'm working with proportions, I'm going to go to this top box here. It literally says sampling distribution for proportions. The first column is for one sample, and notice that very, very first row is for one sample, and that very, very last column is the standard error. So there's the formula for standard error, square root of p hat times 1 minus p hat divided by m. Let me zoom in here so you can see this a little bit better. And then right underneath it is the formula for the standard error when you're looking at the difference between two sample proportions. And then scroll down, and then there's a box in the middle here for the sampling distribution for means. Once again, the top row is for one sample, bottom row is for two samples there, and we got those formulas. Now, the next box is for sampling distribution for linear regression. Now, listen, you will never need this formula for standard error. Trust me, you'll never, ever need it, because if you are going to be asked to construct a confidence interval for a slope, you're going to be given a computer output table. In that table is the standard error. Like, it's literally in the table. It's right next to the slope. It's labeled standard error. There's a column for SE. That's right next to your slope is where you're going to find that standard error formula there. So hopefully that makes sense. All right. So getting kind of back to margin of error in general, Once you construct that margin of error, once you calculate that margin of error, all you got to do is add and subtract it from your sample statistic, whether it be a p-hat or an x-bar or even a slope. All right, so let me take a minute here to kind of look at some more questions. All right, somebody said, when answering probability questions, do we actually have to solve and write out the answer in context, or can we just say probability x equals whatever, and the answer if it doesn't necessarily stay in context? I always tell my students, every time you're asked a probability question, label it, right? But you are allowed to abbreviate. So if you're talking about, what's the probability that a turtle weighs over, 30 grams? Well, just use a T for turtle. So you're going to write P and then in parentheses, T greater than 30. I mean, so in terms of, do you have to write everything out? No, but I will say this, and I don't know if this is exactly what this student meant, but when you're doing a binomial problem, you have to show your work. Now, hold on, let me take a step back. If it's a multiple choice, you don't have to show work at all. Please use your calculator to make your life easy. But if it's a free response question, you definitely want to show your work, but you could use the calculator to do the work. Now, I have a whole series of videos. Again, just look under my videos. You'll see one about the binomial distribution. I actually do a couple problems in there where I show how to use binomial PDF and how to use binomial CDF. And then I talk about what you have to show on an FRQ and then how you can make that easy, but then you just got to go to your calculator to get the answer. So hopefully that answers your question there. Not sure if it did or not, sorry, but hopefully it did a little bit. All right. Let's see here. Somebody says, from a box plot, do we find skew based on the boxes or the tails? Honestly, it's kind of a combination of both. Let me show you what I'm talking about here. I'm going to do a terrible drawing here and see if I could explain what I'm talking about. I'm trying to use 3 different computers here, so this isn't going to be easy. So if you have a box plot that kind of looks like this, all right, that's clearly skewed to the right. We see that not only is the right box, but the right tail are both elongated and skewed to the right. But I mean, that doesn't mean it has to look like that. You could have a box that's pretty nice and even, but then this right tail, wow, that's really bad. But that right tail is just really, really long. That's still going to be skewed right for the most part. But typically, if you're skewed right, you will see that right box and that right tail both be longer width-wise than the left-hand side. And if you're skewed left, it'd be the same thing. So hopefully that makes sense there. All right. All right. People ask, am I going to do a review of every single unit in this video? Probably don't have time for that, but I could speak a little bit about each. Somebody said, can we go over different types of samples? Yeah, we can do this real quick. So the 4 different types of sampling techniques that are good random samples is a simple random sample, stratified random sample, cluster random sample, and a systematic random sample. Now, the 2 that most kids have a hard time differentiating between is stratified and cluster. But let's first start with simple random sample. If your population is high school students and you don't care about anything, you just need to get a group of, say 100 high school students, and it doesn't matter what grade they're in, it doesn't matter their gender, just nothing matters, do a simple random sample. Now, I always tell kids, if you do a simple random sample, you're probably going to get boys and girls. Is it going to be perfectly 50-50? No, but you're probably going to get boys and girls. You're probably going to get a couple freshmen, sophomores, seniors, juniors. Might not all be the same number, but come on, it would be extremely weird if I did get only girls that were freshmen. Now, listen, in a simple random sample, that is certainly possible, and that's what makes it so simple and random, is that any group has a possibility of being selected, even a group of all girls that are freshmen. But stratified is when you're like, well, wait a minute. No, I need to get different genders. I need to get different grades. So maybe you go ahead and create 8 groups: freshman girls, freshman boys, sophomore boys, junior girls, senior boys. And then once you create those groups, and those groups are very heterogeneous, meaning inside they're very, very similar, right? Then what you're going to do is you're going to go ahead and take some from each group. So that's the idea. You're going to take some people from each group. Anytime you see that tagline, take some from each, that's going to be stratified. And what stratified does is it guarantees that representation. Now that group of all freshman girls is impossible to occur, and we're guaranteed to get that representation that we want. Now, cluster random sample is when you create groups And in each group, they are very, very, very different, very different, heterogeneous. Actually, I said the wrong word earlier. When you do a stratified, your groups are very homogeneous. They're very similar within. When you do a cluster, they're very heterogeneous. They're very different within. And each group is like a nice mini population. Therefore, whatever group gets picked doesn't really matter because they're a nice mini population. The example I use with my students all the time is our lunches. At my particular school, we have 4 lunches. And I say the 4 lunches would be a great cluster. All 4 lunches have boys and girls, freshmen, sophomores, juniors, seniors. Any variable you could possibly think of, there's probably going to be in all the different lunches. So then what you do is you label the lunches, lunch 1, lunch 2, lunch 3, lunch 4, and then you select one of the lunches at random to be your entire sample. Now, a cluster sample is an advantage is that they're very quick and easy. You don't have to label all the individuals. You're just labeling the clusters, and then it's much easier to pick. But if you don't set it up right, then, well, it's actually going to be terrible, right? It's not going to be very good at all. For example, if I set it up as a stratified, where I create these groups of freshman girls, freshman boys, sophomore girls, sophomore boys, and so forth, and then I only select one of them to be my entire sample. So I'm doing a cluster sample, but I'm doing it very poorly. I'm not going to get that representation that I need. So, the advantage is, it was fast and easy, but the disadvantage is it's not going to be representative. Typically, we do cluster samples when we already have these pre-made clusters, like I said, the lunches, groups that are already made up that it's nice and easy to pick from. And then the fourth one is systematic, and that's where maybe we get a list of every kid in the school, alphabetical or something like that, and we just pick every 10th kid off the list or every 12th kid off the list, or kids coming into the school one day, we picked every 20th kid coming in. Something along those lines is a systematic sample. All right, let's see what else we got here. When do I use normal CDF? This is another big one that comes up a lot. 2 things. Anytime you're working with z-scores and the distribution is normal, that's when you use normal CDF. So you have to be normally, or your distribution has to be at least approximately normal. Now, if it says the population is normal, well then, knock your socks off, find the mean, get the mean, get the standard deviation. Usually they're going to be given to you, and go ahead and work on that. Get the z-score for a particular value they ask you about. Use normal CDF to look above or below or even in between. Now, I did make a video recently. It's called The Normal Model is King. It's one of my newer videos. So I would actually check that out. So whoever's asking about that question, David, that video goes into all the different ways that we could use the normal model and how to use normal CDF. But again, I want to make sure I say this. Don't ever put normal CDF on your paper for an FRQ question. So let me just share my screen here so I can show you what I'm talking about. If I have a particular problem, I'm given the mean, I'm just going to make up some numbers here. I'm given a standard deviation, and I say, what's the probability that a random value is greater than 16? Okay, so first off, let's start off by labeling the problem, right? Like the probability that something is greater than 16. That's what the question asks. Then what I'm going to do is I need to get the z-score for 16. So how do I get the z-score? I take 16 minus 18. I divide by 2. 16 minus 18 is -2. -2 divided by 2 is, well, the bottom was not a -2, sorry, is -1. So because I'm normal, asking about x being greater than 16 is the same thing as asking about a z-score being greater than -1. Now, as long as the problem stated that that the population that I'm talking about, whatever this 18 and this 2 come from, follows a normal distribution, then I can go ahead and use normal CDF. So grab normal CDF, second vars, and I'm going to look from -1. That's my lower value. I want it to look greater than 16, which is greater than -1. So I'm going to type in a 99. That's actually my infinity. Now, I know somebody's going to ask, and they're going to say, well, wait a minute. Can't you just type in 18 for mu and 2 for sigma, and then the lower value would simply be the 16 you're asked about? Yes, 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 yes. Yes, you could do that, 100%. But you need to show work on an FRQ. Now, if this is multiple choice, go ahead and do that. Actually, you don't have to show work. But there's my probability, 0.841. But notice, this is what they want to see on the exam. They want to see that you identified what the question asks, that you found the z-score, and that you now understand that you're going to use that standard normal model to look at a z-scores greater than -1, and then you get your answer. You do not have to write normal CDF there at all. Now, when you're working with sampling distributions, right? Sampling distributions, as long as all the conditions are met, also follow a normal distribution. So you can also use normal CDF when you're working with sampling distributions if you know that they follow that normal distribution. Now, hopefully that made sense. Let's see here. All right, what else do we got? Somebody said, are we allowed to abbreviate the least squares regression line as LSRL? I tell my students all the time to do that. Honestly, I don't think they would take points off for that. But typically, you're not like in a multiple or in a FRQ question, there's typically not going to be a spot where you would actually write that down. Oh, the least squares regression line. I mean, you may. So using LSR or LR is probably not going to hurt you too much. But I can't think of too many situations where that would actually happen. All right, what else? What else? Somebody's talking about watching my unit review videos. Yeah, I got a lot of good unit review videos out there. I have a playlist called the Ultimate Review playlist. It's got, at this point, probably 60 videos in them, but every unit review video is in there, so that should hopefully help for sure. Let's see here. Trying to look for more questions here that you guys had. All right. A paired t-test is basically when you have like two people that are really similar, or honestly, if it's the same person. Yeah, exactly. A paired t-test is when anytime, you should know what a paired experiment is, right? Anytime you read a problem and it's, you're doing tests, you're working with data that comes from a matched paired experiment, it's going to be a matched paired t-test. And again, can't emphasize enough, the only thing you care about is the differences. Let's see here. Can we go over the difference between a one sample t-test and a one sample t-test? I don't know what they mean by that. Sorry, I don't know if that's a typo there. But I do get a lot of kids that say, what's the difference between a one sample t-test and a one sample z-test? Well, first, if you're working with proportions, always use z. Now, on the calculator, it's a one PROP, one proportion z-test, but it's still a one sample z-test for a population proportion. Like that's the full name that you should be using. Now, if you are working with means and you know the standard deviation of your population, which on the AP exam is never going to be the case, never. But if it was, that's when you do a one sample t-test, one sample z-test for a population mean. But on the AP exam, anytime you're going to be asked to do a test for means, the only standard deviation we know is that of our sample, and that's what triggers the t-distribution to be better. So we do a one sample t-test for a population mean, or a one sample t-interval for a population mean, and so forth. So hopefully that clears that up. That's another very popular question I get. Do you get a formula sheet for the whole thing? Yep. I'm pretty sure you get 2 copies of it. They give you a copy of the formula sheet for the multiple choice questions, and then you turn all that stuff in. And then when you open up the free response questions, you get another copy of that same formula sheet. All right, let's see here. A lot of people are mentioning the Ultimate Review Pack. It helped them out a lot. Yeah, I get a lot of kids that say it's really good. I mean, obviously I made it, so I'm going to say it's really good. But most kids do find it very, very helpful. There's a lot of great problems in there, a lot of great study guides, a lot of great videos. One thing that I put in there recently that I thought was pretty good was that, for the 5 free response questions, the first 5, they are pretty specific in terms of how they're going to look, right? Now, for the past 5 years, they've used the same order, and no one's officially told me they're going to continue with that, but I kind of think they will. The first one is exploring data. The second one's collecting data. The third one is probability and sampling distributions. The fourth one is inference. And the fifth one is usually a combination of 2 or more of those things together. Now, in the Ultimate Review packet, I have packets of each of those types of FRQs with 4 practice problems. So there's a packet for exploring data FRQ, and there are 4 examples. Then there's another one for the collecting data problem with 4 examples. So it's great to practice those questions and do multiple of them, because those are the types of questions you are going to see on the exam. Let's see here. How do we do a confidence interval for slope? All right, this is awesome. It's probably worth it if I go over this real quick, because again, this is almost guaranteed to be a multiple choice question on the exam. One of my more recent videos, top secret AP statistics problems, was a video that I had where I put out about like 5 or 6 like almost yearly questions that are going to be on the exam. So, and this was one of them. So if you're looking for more detail I'm about to give you, please go ahead and check that out. All right, so let me go ahead and share my screen here so I can show you what I'm talking about here. All right, so if you're asked to construct a confidence interval for slope, very, very simple formula. First off, I need my slope. What was the slope from my sample? Then I'm going to go up, I'm going to go down by that margin of error. I need a T star, and I need the standard error for my slope. Okay, here's the best thing. The slope and the standard error are going to be given to you. You do not have to do any work to find them. When you have one of those computer output tables, and I apologize, I should have had one like pulled up and ready to go here. But when you have one of those computer output tables, there's going to be a column that says coefficient. There's going to be a column that says SE. There's going to be a column that says T-score or T-stat, something along those lines. There's going to be a column that says P-value. Again, then there's going to be 2 rows, right? There's going to be the intercept row, and there's going to be the X variable row. Now, in the particular example, it'll be whatever that X variable is. Let's say it's time, or let's say that it's weight, or whatever, it'll be there. Now, in this first column are the slope and the y-intercept, and it goes in alphabetical order, A and then B. So the slope that we're using right here is going to be right there. That's exactly where it's going to be. Now, remember that equation for the least squares regression line is y equals a plus bx. So again, there's the a that you need and there's the b that you need. So again, first column, second value is your slope. Now, directly next to it, literally right next to it, is going to be the standard error. The standard error that you need to put right there is going to be directly next to the slope. So you don't have to do any work to find them. They're there. Now, the only thing you will have to actually find, and this is usually like the difference between choosing the right answer and choosing the wrong answer, is getting the proper T star. So let's talk about that T star. So obviously it's based on your level of confidence. So if you're asked for 95% confident or 98% confident, that's going to affect your T star. But you also need your degrees of freedom. When you go to invert T to get a T star, you need your degrees of freedom. Or even if you use one of those T tables, you need your tail probability, which comes from your level of confidence, but you also need your degrees of freedom. Now, the degrees of freedom when you're working with slope is sample size minus 2. Sample size minus 2. The only time that you're going to subtract 2 for your degrees of freedom. So go to my calculator. I'm going to go second vars, go and grab an invert T. So let's say the question was 98% confidence interval. That means the area at the bottom is 0.01. 98% is in the middle, 2% left out, 1% at the top, 1% at the bottom. And the area it's asking for here is the area at the bottom. And let's say that our sample had 12 in it. So we would have 10 degrees of freedom. 12 minus 2 is 10. And boom, there is the T star that we would need. Ignore the negative. It's only negative because it's at the bottom. The other end would be the positive 2.76. But the plus and minus is accounted for in the formula for confidence, for a confidence interval. That plus and minus is already built in there. So that's it. That's how you get your T star. So again, that's how easy it is to construct a confidence interval for slope. Because the 2 things that are the most difficult are literally there for you in one of these computer output tables. And I know somebody can always say, but what if they don't give me one of these computer output tables? Every single year I've ever seen these problems, they give you a computer output table that has it. The only thing you do have to look up is your T star. And I'm going to tell you, one of the wrong choices will be using sample size minus 1. So please be very careful that you use sample size minus 2 for your degrees of freedom there. All right. As I'm trying to look here for some more questions, just another piece of advice. On the FRQs, always write in context. I always tell my students, If I ask you, did you go to the store last night? Don't just say yes or no. Say, yes, I did go to the store last night. And I bought Oreos and milk, and I went home and I dunked the Oreos in the milk. It was amazing. Or no, I did not go to the store last night. I had a baseball game and I had 3 strikeouts and I stunk. The point is always speak in context. If they ask you a question, answer it, but repeat the question. So they say, is there significant evidence that, just trying to make something up here. Is there significant evidence that the mean weight of a bullfrog is more than 10 grams? Yes, there is significant evidence that the mean weight of a bullfrog is more than 10 grams. Here's the reason why. My p-value is below my alpha level, so I'm going to reject the null. There is statistical evidence that the mean weight of a bullfrog is more than 10 grams. Always answer in full detail and full context. Even on a probability question, use that proper notation. I mean, I guess if they simply say, what is the probability? You just really just need an answer. You don't have to write out a full sentence, but it never hurts to always fully explain yourself. Even on a binomial question, again, if this question is just asking for a probability, but I always tell students, especially if you're like unsure of yourself, if you're like, oh, I'm not sure if I'm doing this right, write something down, right? Like, okay, I know that I'm supposed to find the probability that it's 2 or more. So I'm going to try to find the probability it's 2, 3, 4, 5, 6, 7, or 8. If you know how to do the problem, obviously do the problem. But if you're not sure, write something down. Give the graders something to grade, and it might just give you a chance to do well. But on the first 2 FRQs, which are typically over exploring data and collecting data, you want to write a lot. On that exploring data, you're probably going to be given some type of data plot, like a histogram, a dot plot, a box plot, something along those lines, and you're going to be asked to describe it. Or even if it's a scatter plot, you're going to be asked to describe the distribution. Write, describe it, use context, right? The data, don't just say it's skewed left, it has a center of 0, and it's spread. Like, use context, right? Say the distribution of weights of bullfrogs is skewed to the right. Where there are very few heavy bullfrogs, most bullfrogs are at the bottom, having a center around 10 grams. But there's a couple bullfrogs that are really, really, really high on that high side, making it skew to the right. The data is spread all the way from a min of 2 grams to a max of 100 grams. But if you actually look, the majority of bullfrogs weigh 10 to 20 grams. Always talking about bullfrogs, if that's what the question's about. Same thing with the collecting data problem, right? The collecting data problem is either going to be about collecting data, different sampling techniques, or maybe bias, or it's going to be about an experiment. Use context, constantly using words that are from the problem. And the other thing I always tell students, especially if you're using a significance test or an interval, they're going to tell you in the problem, like, hey, construct a confidence interval for the population mean weight of African bullfrogs. So when you give your interpretation, make sure that you use those exact same words. Don't make up stuff on your own. Copy from the problem. So say, hey, I'm 95% confident that the true mean weight of African bullfrogs is between 9.6 and 11.7 grams. Like, use the words from the problem to answer it. Don't try to make your own stuff up, especially for chi-square tests as well. The question is going to have the problem in it. So just repeat that for your null and your alternative hypothesis. It's all going to be in there. All right. A lot of people saying they're nervous. They don't know if they're going to, somebody just asked this right here. When is t n minus 2? So again, that's the degrees of freedom for a slope. Degrees of freedom when you're working with slope, you're going to use n minus 2 degrees of freedom. Another question that comes up a lot is, what about degrees of freedom for 2 sample t-test or 2 sample t interval? There are 3 different ways to find degrees of freedom in that situation. 1, use the formula. There is a very complicated, extremely ugly formula for degrees of freedom. It's comical to me, like the degrees of freedom formula for 1 sample is so easy. Sample size minus 1. Like, it doesn't get any simpler than that. But the moment there's 2 samples, it's like this crazy complicated formula. You don't ever have to use that formula. Like, literally, I don't even show my students the formula. There are 2 options that are fully acceptable. You could take the degrees of freedom from each of your samples. So maybe one sample's 10 and one sample's 8. So you have 7 degrees of freedom and 9 degrees of freedom. Use the smaller of the 2. So I'd use 7 degrees of freedom, the smaller of the 2, totally acceptable. Or you could take those degrees of freedom and add them together. So you take the 7 and the 9 and add them together to get 16, use 16 degrees of freedom. Both would be fully acceptable on the AP exam. All right. Somebody said chi-square tests. Unfortunately, I already spoke about that in the very beginning, about the different types of chi-square tests. Yep, somebody said standard errors are right next to the slope on the computer-generated boxes. Yep, exactly. Let's see here, some of the more recent ones. Oh, boy, what else? I'm just trying to get there. A lot of people making just some generic comments. Thank you, yada, yada, yada. I'm trying to get through all that. Okay, here's the same question I get a lot. Okay with calculator functions inputs for showing work on FRQs. Would you recommend using calculations or calculator functions? So again, there's all different kinds of responses to this. I always tell students, show your work. You could use the calculator to do your work, but show your work. But listen, if you're doing a problem and you're trying to find, the probability that a sample proportion is more than 18%, and you get the z-score, maybe the z-score, you look up that z-score, and that z-score is, I'm just making this up, is 2.14. If you're going to go to normal CDF to get this answer, right, you are allowed to write on your paper. Like I mentioned earlier, I wouldn't do it, but you are allowed to write normal CDF. Now, what you then have to do is you got to label everything, right? So you got to put 2.14. That's my z-score, all the way towards infinity. And then the mean is 0. The standard deviation is 1. This is the mean of the standard normal model. This is the standard deviation of the standard normal model. Like, that's awesome. But again, I tell my students, you don't have to write all that out. But if you do, they want everything to be labeled. What you need to do more than anything is to really do a good job of labeling your tests. This is a one sample z-test for a population proportion. That matters so much. And then if you do use your calculator and you get a t-score of 2.14 and you get a p-value, and again, I'm just going to make this up, 0.0027, that's it. You could use the calculator to show that work. What really matters most is that you labeled the tests, you had all of the conditions checked, and then you're going to have your hypotheses, and then you're going to give that really good conclusion based on those values. That matters so much more if you're doing it all correctly. So hopefully that makes sense, because a lot of people ask that. Even for the binomial problems, if you're doing binomial PDF or CDF, show your work. But if you want to go to binomial PDF to do the work or binomial CDF to do the work, by all means, but they want to see that work shown. Let's see here. Somebody wrote, shout out to Barron's for being awesome, by the way. I'm assuming you're meaning to the Barron's review book. Yeah, those Barron's review books are really, really good. I would recommend them too. Let's see here. Z-score formula, please. Somebody wrote. Okay, I'll go over the Z-score formula. Somebody emailed me the other day. Can you explain to me how to use a Z-score? I wasn't trying to be mean to somebody. I said, boy, if you don't know how to use a Z-score, you're a little bit behind the game, right? Okay, so Z-score formula is taking a particular value minus the mean and divided by the standard deviation. Now, it's important for me to say this real quick. You do not need to be normal to calculate a Z-score. Anytime you have a mean, a standard deviation, you can find a Z-score. Like I have 90 students in AP statistics, right? And if I give a test, I have 90 scores. It doesn't matter if that distribution is skewed left, skewed right, or normal. It doesn't matter whatsoever. I could say, oh, hey, Sally, your Z-score was 2.3. That means Sally did 2.3 standard deviations above the mean. Sally did really, really good. That's awesome. So that Z-score, whether it doesn't even matter what the shape is, she knows that she did 2.3 standard deviations above the mean. That's awesome. That would actually be considered an outlier. Most kids are within 1 standard deviation of the mean. The fact that she's more than 2, it tells her how good she is. Now, the formula, if now you can talk about different types of formulas here, right? Like if you're working with a particular value and the mean is the population mean, the standard deviation is the population standard deviation, then there you go. There's your formula for Z-scores. If you're working with a sampling distribution, then you have your p hat minus the mean of all the p-hats, that's the center of your sampling distribution, divided by the standard deviation of your sampling distribution. I mean, it's that simple. It makes a lot of sense. But you have to be able to say, oh yeah, I know how to find the mean of my sampling distribution and the standard deviation of my sampling distribution. But again, it's the idea that I'm taking a value minus the mean divided by the standard deviation, whether it's coming from a population that's normal or whether it's coming from a sampling distribution. All simple, all easy there. So hopefully that makes sense. I don't know if I answered your question or not, but I'm trying. All right, another water break. All right, how to make hypotheses for slope. Okay, great question. Let's go over this. Now, again, I'm going to be honest, very unlikely, but not impossible, to see a test for regression line on the exam. If it does come up, usually it's like bare bones, just do some of the minor work. One year there was a test for slope, but they actually did all the work for you. Really, they just wanted you to interpret the p-value, and hopefully you know how to do that. But let's quickly talk about it. Now, when you are talking about slope, typically we're asking, is there a slope? Like, if you have a sample of data, and you put a line through it, that line's going to have a slope, right? There is a slope of your line. But if we looked at the entire population, not just 10 dots, is there a slope? Well, that's what we want to figure out. So the null hypothesis would be that the true population slope, which we call beta, is equal to 0. So we would assume there's no slope. Now, if there's a slope of 0, that means that your two variables are not connected together whatsoever. X has nothing to do with Y. Y has nothing to do with X. If your slope is 0, then X goes up and Y doesn't do anything. You know what I mean? So that's why the null is that the slope is 0, because we're basically saying, hey, we're going to assume that there is no relationship whatsoever, which is a slope of 0. And then the alternative would be, no, there is a slope. Beta is greater than 0. Now, obviously, I'm going to use greater than 0 if in my scatter plot I see a slope that's going up. If you had a scatter plot that was going down, then you would say, oh, no, I think there's a slope that's less than 0. But again, greater than 0, less than 0, you're saying that there is a slope. So that's going to be your null and alternative when you are working with slope. Now, when you have one of those computer output tables, right next to the slope is the standard error of the slope. Right next to that is your t-score, and right next to that is your p-value. So literally, you don't even have to do any work to find the t-score or the p-value. Everything is right there for you. You don't have to do any work. It's there for you just to find the p-value. Now, I will say this. This is really important to hear. The p-value given to you in one of those computer output tables for linear regression is based on a null of the slope being equal to 0 and an alternative of it being not equal to 0, right? Because if we don't care, all we're saying is there a slope in our data? I don't even care if it's positive. I don't even care if it's negative. I just want to know, is there a slope? Then our alternative would be not equal to. Now, usually in most problems, like, hey, we're saying, hey, the slope is positive. Is there really a positive slope in the population? Or, hey, our slope is negative. Is there really a negative slope in the population? We would actually wanting it to be greater than or equal to 0. But again, that's what you have to understand. When you have an alternative of a not equal to sign, that's when you double your p-value. So the p-value given to you in one of these tables, it's already been doubled. So if your alternative is greater than, you would just take that p-value and cut it in half. Okay. Now, that's not to say that there isn't problems out there where somebody says, oh, I think the slope is 2,000, but I think it's more than 2,000. Okay, well, if that's the case, then the null would be, wrong symbol there, sorry. Now, this doesn't happen very often, so I'm just being honest here, but you'd say, oh, the slope is 2,000, that's the null, and the alternative is that the true slope is greater than 2,000, something along those lines. You don't have to have a 0 there. But in a computer output table, the t-score and the p-value given to you is based on a null of 0 and an alternative of not equal to 0. So a problem like this, where the slope is 2,000 and we're trying to show the slope is greater than 2,000, that's just not going to happen on the test, to be quite honest with you. It's extremely unlikely to happen. So hopefully that answered your questions about that. I'm not really sure, but hopefully it did. All right. And I should have been more prepared here with some more examples to show you guys. And maybe if I do one of these again on Monday morning before the exam, maybe around 8:30, 9 a.m. Eastern Standard Time, maybe I'll try to have a couple more examples kind of up and running to show you guys. Let's see here. My teacher said she's going to be really disappointed if I get below a 3. No, it's okay. I always tell my students, listen, I don't care how you do on the exam. I hope I've taught you enough to get a 3, 4, or 5. But at the end of the day, it's your grade. You know, I mean, you just have to own it. It doesn't really, no one's going to fire me if you guys don't do well. Somebody said yes. I mentioned this, right? The College Board videos do say that you can show calculator commands as long as you label everything. But what happens is a lot of kids don't label everything, and that's where they run into a problem. So I'm not saying that you can't do that. You certainly can. But the most important thing, especially with the test or an interval, is naming it. Like the value in that is so important. If you don't name, hey, I'm going to do a 2 sample T interval for the difference between the mean amount of time girls spend on homework per night and the mean amount of time boys spend on homework per night at a particular high school. That right there is important. That is so important to label and name what it is you're doing. Then if you use your calculator to find your interval, well, that's awesome. Then you got to interpret your interval. That's really important as well. So, I'm not trying to say, use the calculator commands. By all means, they're going to really save you a lot of time, especially on multiple choice. But, if you are going to show them on the screen or on your test, you do got to label everything. Let's see here. I'm going to use my abacus. That's where I calculator. I like that comment. I actually have an abacus hanging in my classroom. Oh boy. Trying to read for some good questions here. And, just as I'm trying to find more questions here, speaking about the the FRQ questions, honestly, they're usually easy. Like, I really mean that. Like, especially the last couple of years, I think they're really easy. But even if you get 2 out of 4 points on the first 5 FRQs, you're doing really, really well. That's going to push you or project you towards getting a passing score of a 3. So don't panic if you don't get everything right or you walk away like, oh, I got everything wrong. Just get a couple points on every single question and you're going to be fine. I'm trying to find more comments here. All right, somebody said, is the null always supposed to be equal? I've seen many answers where the null contain inequality. I mean, in some advanced statistics, you could use an inequality for the null, but I'm going to tell you right now, the null should always be an equal sign. It really, really should. It should always be an equal size. The mu equals 18, and then the alternative could be less than, greater than, or not equal to, or for proportion-based, p equals 0.12. You really should never use anything besides an equal sign on the null and the null hypothesis. Let's see here. If the population is known to be normal, can we use z-test without knowing the population standard deviation? No. If the only standard deviation you know in the problem is the standard deviation of your sample, S, not sigma, then you need to use a t-test, not a z-test. William Gossett was the statistician that invented the t-distribution, and he invented it because of the fact that when you don't know the population standard deviation, using z-intervals, using z-tests is just not as accurate. So when you are using S, the standard deviation of your sample, you need to be using a z-test or a z-interval. If you have a TI Inspire and write calculator command and you have lower and upper, can you include that, or do you have to label it with the TI-84? You don't have to write lower and upper. You just have to label it lower and upper, which I guess means you're writing lower and upper. So kind of yes, But so a lot of kids will be like, well, I'm just going to copy the calculator screen. Like I'm just going to like literally make like a little square and I'm going to show exactly what I typed to the calculator screen. I would not recommend doing that, right? That's definitely what I would call calculator talk. I would not recommend doing that at all. Somebody said, can you explain the difference between chi-squareds? I'm sorry, I did talk about that in the beginning of the video. So if you go back and rewatch the beginning, I talked about that. Type 1 and type 2 error. Yeah. Type 1 error is when the null is true. The error is that we reject it. Yeah, so that's good. Let's see here. The comments are coming so fast. I'm sorry, I don't have time to read them. Can you explain the difference between standard deviation and standard error? Yes. So I call them twin brothers because, you know, if you look at, let me actually pull up the formula sheet here so I can show exactly what I'm talking about. So for example, if we look right here for proportions, right? This column right here in the middle is using sigma, right? The standard deviation of the sampling distribution, okay? This is basically saying if you build a sampling distribution for sample proportions, there's going to be lots of different sample proportions, okay? And they're going to vary. You know, the mean of all of those sample proportions should be the true population proportion P. That's the first column. But we know that those sample proportions are going to vary. Some are going to be more than the truth. Some are going to be less than the truth. So how are they going to vary? How can we measure that variation is with the standard deviation. But notice the standard deviation formula requires the true P, the population proportion. Now, what if we don't know that? What if we don't know the population proportion? Then we use standard error. And that's that third column here. So when we replace that P with P hat, it's we use standard error. So I always say think of it as like the next best thing. Standard deviation is obviously preferred, but the next best thing is the twin brother because it's the exact same formula. All we're doing is changing P to P hat, and that's what we call it standard error. So standard error is used in a confidence interval or a significance test because we're saying, hey, all we have is our sample data, so we want to get a good estimate of what that standard deviation could be, even though we don't know it. And then even when we go down here in this chart here for means, same thing. In the middle is the standard deviation of a sampling distribution for sample means. So a sampling distribution for sample means is filled with sample means, and the mean of all those X bars should be the population mean, mu. That's that first column. But all of those different sample means are going to vary. So how are they going to vary? How can we measure that variation? Well, that's where we have the standard deviation of the sampling distribution, X bar, and we have the standard deviation of the population on top divided by the square root of our sample size. But as I've mentioned multiple times, if we do not know the standard deviation of our population, then we have to use standard error, which is simply replacing the standard deviation of the population with S, the standard deviation of our sample. Now, in a lot of problems, you might know the standard deviation of the population. That's going to allow you to create probabilities, especially for a sampling distribution. But if you're doing a test or an interval for a mean, and all you have is the data from your sample, the mean of your sample and the standard deviation of your sample, you're going to be using the T. That's the whole point of talking about that. All right, so hopefully I answered that question. What else here? How to put binomial inequalities in the calculator. What is it less than? What is it greater than, etc. Okay, let me talk about this real quick. Again, I do have a video over this. It's one of my calculator videos that talks about this, but I'll definitely go over and show you guys this right now. All right, let's pull this up here. Sorry, I'm trying to create a blank space here. Hope everybody can see my screen okay here. Again, this is my first time live streaming, so I'm trying to do it properly, but it's probably not great. Okay, so let's say that we have 8 trials. The probability of success is 75%. Okay, so let's say that I'm going to shoot 8 free throws, and I have a 75% chance to make any one of those free throws. Now, assuming that every shot is independent of the next. That means I can make 0 free throws, 1, 2, 3, 4, 5, 6, 7, or I can make 8 all free throws. I can't make 9 free throws. I'm only shooting 8. And I can't make a negative amount of free throws. It's impossible. So if I said to you, what's the probability that I make 3 free throws? Okay, so I'm finding the probability that X, the number of free throws I make, is equal to 3. And using the formula, because again, you got to show your work on FRQ, is 8, choose 3. That's going to tell me how many different combinations. Like, do I make the first 3? Do I make the last 3? Do I make the first one? Do I make the third? And then I make the 8th? How many different combinations you can make 3? Now, I need 3 successes. So I need 0.75 to the third because I need 3 of them to be makes. And then I need 0.25 to the fifth because if there's 3 makes, oh man, hold on a minute. I just accidentally closed out of that. I'm so sorry. Bad timing. Here we go. Oh boy, I'm sorry. Click the wrong button and that's what happens. Okay, so back to the problem. Sorry about that. All right, so once again, 8, P was 0.75. Okay, so if I'm trying to find the probability that I make exactly 3 shots, once again, 8, choose 3, 0.75 to the third, and then times 0.25 to the fifth. Okay, now, I'm not going to waste my time trying to, I want to show that work, but I'm not going to waste my time trying to do all that work by hand. That's where I'm going to go and grab a binomial PDF. Now, if you showed all of your work like I just did, you don't have to write binomial PDF and label everything you type in because you already showed your work. A binomial PDF will do exactly what you tell it. So I'm going to type in 8 trials. Probability of success is 0.75. And I wanted to find the probability of exactly 3 makes. And boom, there it is, 0.023. Done. Again, do I have to show what I typed on the calculator? No, because I'm showing my work. Here's my work. Here's my answer. You don't have to type in, you don't have to show anything about what you did in the calculator. All right. Now, remember, I can make 0, 1, 2, 3, 4, 5, 6, 7, or 8. Okay. What if the question says, what's the probability that you make less than 3? Less than 3. Now, what's less than 3? 0 is less than 3. 1 is less than 3. 2 is less than 3. 3 is not less than 3. Now, if it said or equal to 3, well, then, yeah, I would need to include 3. But what do I do here? Well, now I got to show my work. 8, choose 0. 8, choose 1. Or 8, choose 2. That would be 0 makes. That's a 0.75 there. Sorry if I'm messy handwriting. And 0.25 to the 8th. All 8 are make or misses. 0.75 to the first. 0.25 to the 7th. Or 0.75 to the second, 0.25 to the 6th. And I'm going to add all of these together. Now, there it is. There's me showing my work. That wasn't too hard. But now I'm going to go to my calculator, and I'm going to do second vars. Now, this is where binomial CDF is going to come in handy. Now, CDF will do whatever X value you type in and anything below it. So 8 trials. Probability of success is 0.75. And then if I type in a 2 here, it's going to do 2, 1, and 0 and add them all together for me. Don't type in a 3 unless you want to include 3. But if the question says specifically less than 3, I don't want to type in 3. So then go ahead and hit enter on the calculator, and there's your answer, 0.004. But again, do I have to show what I typed in the calculator? No, because you showed your work. They don't care how you got your answer as long as you showed your work. So there's my work. That's how I showed it. Okay, what if they say, what's the probability that X is greater than 3? Okay, what's greater than 3? 4, 5, 6, 7, 8. Now, what can I do? Well, CDF goes down, not up. So what I could do here is I got to show my work. So I could show the work for 8, choose 4, 8, choose 5, 8, choose 6, 8, choose 7, 8, choose 8. I mean, there'd be 5 things. That might take a little bit of time, and it wouldn't take forever. And then I could add them all together, and I could do a PDF for 4, a PDF for 5, a PDF for 6, a PDF for 7, a PDF for 8. get those answers and add them together. That would get it. Or I could find what I don't want. What I don't want is 3, 2, 1, or 0. I could find this, but if I go that route, I have to do 1 minus it. So I'm going to do 1 minus the probability that x is less than or equal to 3. That, if I get rid of these from 1, then I'll be left with 4, 5, 6, 7, 8. Now, again, how am I going to do that very quickly on my calculator? Well, that's the whole point of what a CDF could do very quickly for us. So if I go down to binomial CDF and I type in 8 shots, 0.75, and this time I type in 3. Oh, type in 3 there. This is going to calculate 3, 2, 1, and 0 for me. But remember, this is what I didn't want. I wanted greater than 3. Greater than 3 is 4, 5, 6, 7, 8. So I'm going to do 1, which is 100%, minus that value, and I'm left with my answer. So there's my answer for greater than 3 makes. So hopefully that made sense of how we could utilize binomial PDF and binomial CDF to make answering binomial questions pretty easy for you. But if you show your work, you don't have to label. Now, as people mentioned, you are allowed to show the binomial. For example, if I'm doing the probability that x equals 5, right? Binomial PDF, and I'm going to type in 8.75 and then 5. Now, this is where you do have to label it. Say, hey, this is n, my total number of shots. Here's my p, my probability of success. Here's x, the number I'm looking for. You do have to label all that. You can do it that way if you want. But again, I like to tell students, use the formula. Because guess what? Let me show you this real quick. It's on the formula sheet. Right there in the middle is the formula right there that I just went through for the binomial distribution. So utilize the formula, and then you don't have to show any calculator work at all. You could use the calculator to get your answers. What the heck is that? But you don't have to do any of the work because your calculator is going to do it all for you. Okay, hopefully that made sense. Can you explain observed versus test statistic? So I'm not 100% sure what we mean by that question, but actually, if we look at the formula sheet, let me jump over and show it real quick here. All right, so a test statistic. This is the most generic formula for a test statistic. It's taking a statistic from a sample, which is considered an observed value. A statistic is anything that comes from a sample. If it came from a sample, it means you observed it. So that's your observed value. The statistic is your observed. And we're going to subtract the parameter. What's a parameter? A parameter is anything that, we were told was true, or we thought was true, or was supposedly true, but we think it's something more, or we think it's something less, or we think it's just something different. Now, in any kind of one sample test, that parameter is going to be given to you. Like maybe you read 80% of people recycle, but you think it's less. Or maybe you read that the population mean weight of a bullfrog is 80 grams, but you think it's less. That's what you're going to put there. But in a 2-sample z-test or a 2-sample t-test, when you're looking at difference, the parameter is always 0 because we assume that there is no difference whatsoever, and therefore that parameter value is 0. And then the statistic would be the observed difference that we saw. And then, of course, to get that test statistic, you divide by your standard error. And how do you know what standard error to use? Well, go to the next page of that formula sheet. There's an entire column here for standard error. All you have to know, are you working with proportions or are you working with means? 1 sample or 2 sample, it's going to direct you exactly to where you need to be. All right, I got about another 12 minutes and I got to go. Sorry. Let's see here. How to put different binomial inequalities in the calculator, what if it's less than, what it's greater than. Oh, that's what I just did. So hopefully that made sense. Somebody was answering somebody else there. Sorry. Live stream is good. That's good. I appreciate it, even though it's my first one. Now, I know it's too late for you guys, but my plan next year is to do live streams throughout the whole year. Usually could kind of time it up when the different units are going to be, kind of go from there. Okay, here we go. Say you have a sample, and based on that sample, you want to create a confidence interval to find the true population mean. Say the mean of my sample is like 4. Would it be X bar or mu sub X bar? Oh, that's a great question. It would be X bar. So let's talk about notation real quick, because this is actually something that I have to discuss with my students like on like a weekly basis, because it's so easy to mess up your symbols here. Okay, so what is the population proportion, right? The parameter, the proportion from entire population. Like let's say we knew that 32% of all teenagers vape, that would be a P. But let's say that we get a sample, okay? And in a sample of 1,000 kids, 35% vape. Well, that's called a P hat. So we got our population proportion P, sample proportion P hat. Now, if we're building a sampling distribution to show not just what our sample proportion is, but what all possible sample proportions could be of the same sample size, taken from the same population, then the mean of all of those P hats would be the center. And that mean should be the true population proportion P. But again, this symbol here, mu sub P hat, that is the symbol for the sampling distribution mean. And a sampling distribution is not filled with one P hat, it's filled with millions of P hats. So again, it's the mean of all of them. Now, same thing with population means. If you read that the mean weight of all bullfrogs, I don't know why I keep saying bullfrogs, no idea. What the mean weight of all bullfrogs is, that's going to be mu. That's the population mean of all the bullfrogs. If you get a sample of, let's say, 30 bullfrogs, and from that sample, you calculate the mean of that sample. Simple. Now, that in a test would be your observed statistic. Now, what is the mean of the sampling distribution? Well, again, a sampling distribution doesn't just show one X bar, it shows millions of X bars, every different possible sample mean weight of a sample of 30 bullfrogs, and that symbol is going to be mu sub X bar. That's the mean of all the X bars. That's the center of our sampling distribution. And that center should be the population mean mu, as long as our samples are random. So again, that's where that symbol comes into play. So if you're talking about a test and you have a sample, like you said, and the mean of your sample is 4, well, then you want to label that as X bar equals 4. Now, the p-value of your test is going to be the probability that any other sample mean is more extreme than yours. Now, if yours was on the high side, then you would say greater than 4. If yours was on the low side, you'd use less than 4. So that's why you do have to know, what you assumed to be true from that null hypothesis. So if your null hypothesis was 5 and you found a sample mean of 4, then you'd want to use a less than sign. Or if your null hypothesis was, 3 and your sample was 4 and your alternative was that you believe it's greater than that, then you'd use a greater than 4 sign. So hopefully that answered your question. I'm sorry if it didn't, but hopefully it did, about using proper symbols and when to use them. All right. Can you go over all the conditions how you'd want to word on an FRQ? Great question. Great question. So the first condition, I write this every single time. I teach my students to write it just like a script. The first condition is my sample of 30 bullfrogs was random to avoid bias. My sample of 1,000 teenagers was random to avoid bias. Your samples have to be random. Very simple script there. That's what I'd write down. But I would use context, right? Don't just say it is less or it is random. Say, my sample of 1,000 students is random. My sample of 30 bullfrogs is random to avoid bias. That's the first condition. Sorry. Second condition is only needed if you are sampling from a population. If you're taking a random sample out of a population, you need to check that 10% condition. So we need our sample size to be under 10% of the population so that we can assume independence. So many kids never learn what that 10% condition is all about. But the idea is that when we need our samples to be independent of each other, right? If that sampling distribution is going to properly show what all possible sample means or sample proportions could look like, the samples have to be independent. Now, if we sample with replacement, that's guaranteed. But in the real world, we typically don't sample with replacement. So that's what we say. It's okay as long as our sample size is under 10% of the population. Technically, because you didn't replace, you are violating independence. But as long as your sample is under 10% of the population, it's okay. The difference is negligible. We don't worry about it as long as your sample is under 10% of the population. So if you're sampling in that particular question, I would make sure I say, my sample size of 30 bullfrogs is under 10%, or I assume it to be under 10% of the entire population of bullfrogs, so I can assume independence. Again, notice the context in that statement. I didn't just say it is under 10% and stop there. My sample of 1,000 teenagers is under 10% of all teenagers in the state of Tennessee, so that I could assume independence. That's what you want to make sure you say there. Now, if it's an experiment-based problem, where we had 100 volunteers and 50 of them randomly got treatment A and 50 randomly got treatment B, then you don't have to check that 10% condition because you weren't sampling from the population. Okay, then the third condition is that your sample needs to be big enough. Now, if you're working with proportions to prove that your sample is big enough, you have to show that there are 10 or more successes and 10 or more failures. So what I would do is I would say, hey, my sample of 1,000 teenagers had 35% that were supposed to vape. 35% of 1,000 is 350. That is more than 10. And then the remaining 650 did not vape. So there's more than 10 failures as well. Again, showing that work using context in that question. Now, if you're working with means, being big enough means a couple things. One, any sample size is big enough if your population is already normal. So you could build a sampling distribution with sample means from samples of size 2, as long as that population that those samples came from was normal. If your population is non-normal or maybe just unknown, like it's skewed left or skewed right, or you don't even know what it is, then your central limit theorem says your sample sizes have to be 30 or larger. So you would simply say, hey, my sample of bullfrogs was 30 or larger, so I can assume that I'm big enough. The third condition could also be met one more way, and that is if you're under 30 and your population is unknown, then you simply have to say, hey, I checked my data, I made a histogram, I made a dot plot, something along those lines, I made a box plot, and there's no major outliers and no major skewness, so I'm still okay to be big enough. So hopefully that answered that question in terms of going over the conditions. But those are the three conditions that are pretty important on every single test or interval. Unless you get that freebie, which does happen every now and then on the AP exam, it'll say assume all conditions are met, and you don't have to check them. All right, couple more minutes here, and then I gotta run. Okay. What are the different ways to find degrees of freedom that we should know for the test? Okay, so if you're working with one sample, degrees of freedom is sample size minus 1. Easy. Now, okay, let me backtrack for 1 second. If you're working with means, maybe actually, let me actually show you this so I can kind of write it down as I go here. All right, so if you're working with a problem that is dealing with sample means, and there's only one sample, I'm so bad at writing, then your degrees of freedom is your sample size minus 1. That's simple. If you're working with two samples, the formula for degrees of freedom is extremely complicated, very ugly. What I usually tell kids to do is take the first sample, subtract 1, take the second sample, subtract 1, and add those together. Or you could take the smaller of the two, but I usually tell my kids to just add those together. Pretty simple there. All right, when you're working with slope, if you have a problem that's dealing with the slope of a regression line, you're going to do sample size minus 2 for your degrees of freedom. Okay. If you're working with chi-squared, goodness of fit tests, it's categories minus 1. So goodness of fit tests, you have one variable, maybe you have 5 categories, red, blue, violet, green, yellow. Categories minus 1, so 5 minus 1 would be 4 degrees of freedom. If you're doing a chi-square test with a two-way table for independence or homogeneity, then it's going to be the first variable categories minus 1 multiplied by the second variable's categories minus 1. So you take how many categories your first variable had, minus 1. Take your second variable, how many categories did it have, minus 1. Multiply those two together to get your degrees of freedom. So Great question. Hopefully I answered that one. All right. Let's see here. For 2 sample, can we also use our calculator to find the degrees of freedom? Yes. If you're going to use your calculator to do all the work for you, it's going to give you the degrees of freedom. So if you type in, the mean and the standard deviation of your first sample, the mean, the standard deviation of your second sample, when you go ahead and hit enter, you're going to get your t-score, you're going to get your p-value, and you're going to get your degrees of freedom as well. So it's all there for you. I feel like I always can't make my answers clear for that FRQ. What should I do if my head goes blank for a question I don't know what to put? Boy, that's a good question. I mean, listen, it happens to the best of us, happens to me. Sometimes you're like, I know what I'm supposed to do here, but I just don't remember. It's hard to answer that question. But I always tell kids this, like, the fourth question is typically going to be an inference question. You're going to do an interval, you're going to do a test. Let's say you panic and you just don't remember how to get your t-score, your z-score, your p-value. Just make one up. Just make one up. My p-value is 0.0000694. Just make up a number. Then maybe you do remember how to give a conclusion. Because my p-value is well below 0.01, I'm going to reject the null. There is significant evidence that the true mean weight of bullfrogs is less than 80 grams. I keep using bullfrogs in my examples today. I don't know why. So again, maybe you did remember how to make that conclusion. You just couldn't remember how to get the p-value. I mean, you might still get some points for that. Most kids remember how to do the null and alternative hypothesis, so hopefully you can get some points from that. So, if you just go for complete blank, put something down, try to do something that sounds like it could be, remotely right. What are likely AP predictions? Like, what is going to be question 5? Investigate task, multiple choice based heavily on. Boy, it really deviates for every single year. There's no way I could possibly answer that question. Like I said, we do know 5 FRQs, and they have gone in this order for like the past 6 years. Number 1, exploring data. You're going to see histograms, box plots, dot plots, stem plots, or scatter plots. Number 2, collecting data. It's going to deal with an experiment. It's going to ask you about random assignment, use of placebo, all the kind of experiment stuff, experimental units, treatments, response variables, or it could be about collecting data like a stratified versus cluster, advantages, disadvantages, something along those lines. Third question is going to be probability question. Fourth question is going to deal with inference, where you're going to do a test or a interval. And the fifth question is going to be some type of combination of those things. Now, most kids get scared like, oh, that fifth question is going to be hard because it's a combination. Usually the fifth question is actually easier because it involves multiple things. They can't dive too far into one of them. They just kind of have you skim the surface of 2 different topics. So usually that's not too bad. But predictions, I really don't have any. It's hard to say. And number 6 is just impossible to predict. The multiple choice, again, every single year, they do give the breakdown, the course and exam description in terms of like what percentage of questions come from each unit. It is pretty heavy on unit 1. There is a lot of questions out of unit 1 that are usually pretty easy. And then the units on inference, unit 6, 7, 8 with chi-squared are very, a lot of questions there as well. Somebody wrote question 6, basically everything combined, right? I mean, maybe not. I mean, one year question 6 was like a time plot for hurricanes, and it was like so easy. Like it was unbelievably easy. I was like, I couldn't believe that was a number 6. So it really all depends. But usually there is some type of graph in number 6. And usually part A is just asking you to talk about that graph. So usually it's not too bad to at least get a couple points. I always tell kids, if you just get 1 point on number 6, it's going to really, really help you. Minimum sample size. There isn't one. You know what matters most with samples is it's random and representative. That matters way more than the size of the sample. If it's random and representative, it can be a sample size of 100 or 150, and it's a really good sample to use. Now, if you're trying to go for those conditions, though, well, then the sample size does matter because you need to have enough successes and failures to meet those conditions for a test. What do we recommend you do in the last few days? Somebody said. Honestly, just as many problems as possible. as many practice problems as possible. Get some practice multiple choice exams, whether you use mine from the Ultimate Review Packet, or you use the Barron's book, or you use something that your teacher might assign to you in the AP classroom. Just doing as many multiple choice questions as possible is going to help you. And like I said, in the Ultimate Review Packet, I put together 4 collecting data FRQs, 4 inference FRQs, 4 exploring data FRQs. Just seeing those different questions, how things are worded, can really help you. All right, let's see here. A couple more, and then I got to go. How to explain type 2 error going up, down. Okay, if I'm going to talk about this, I have to talk about power. So power is the alternative is true. And we conclude that. Okay? The alternative is true, and we conclude that. If I want, which is the complete opposite of type 2 error. Type 2 error, the alternative is true, but we failed to reject the null. So we kept an alternative we kept a null that was wrong. That's type 2 error. So if we want more power, we could do a couple different things. One, increase your sample size. Because if the alternative is true, a bigger sample, which varies less, should be closer to the truth. And if the truth is that the alternative is true, a bigger sample should show us that more clearly. Second way is to increase alpha. Alpha is the significance level. It's the rejection area. So if we go from a 1% rejection area to a 5% rejection area, we're increasing our level of significance, which means we're making the window to reject bigger. But if we're supposed to reject because the alternative is true, then we want that window to be bigger, giving us more area to reject, which means we're going to reject the null and go with the alternative that's true, hence giving us more power. Now, if you increase alpha, you're increasing type 1 error, because type 1 error is the probability of alpha as well. So not only is alpha your significance level, it's also the probability of a type 1 error. But we're not worried about a type 1 error if we know the alternative is true. That's the whole point. The alternative is true. So I'm not worried about a type 1 error because I want to make sure I reject the null because it's wrong if I'm going with power. Now, the third and final way to get power is really more out of our control. It's if the truth is further from the null. So if your null hypothesis is that mu equals 8 and the truth is that mu is 27, then you're going to have more power, because if the truth is 27, a good sample, heck, even a small sample, should show that, and hence you'd reject the null. But if the truth is 9, which is only a little bit bigger than 8, you're going to have less power, because even though the truth is still more than 8, the alternative is true, mu is more than 8. But if it's only a little bit more, it might be harder for you to see that, which is going to give you a little bit less power. So hopefully that answered that question, kind of. What should we study heavily in Unit 1? The biggest thing that comes out of Unit 1 is just knowing how to describe a quantitative graph. Looking at a graph and saying, oh, that graph is skewed left, that graph is skewed right, that graph is unimodal, bimodal, there's a gap in the middle, the center is 76, just being able to describe it in context. Talk about spread. The data ranges from 90 to 140, but the majority of data is from 100 to 110. Just being able to say those types of things is so important. The other two big things I would say that come out of Unit 1 is know how the mean and the median compare. When you're skewed right, the mean is higher than the median, because the mean is going to go towards that skewness. When you're skewed left, the mean is going to go lower than the median because it's going towards that bottom skewness. And then how to find outliers. Knowing the fence method to find outliers, or the standard deviation method to find outliers. Now, if you only know Q3 and Q1, well, then you got to use the fence method to find outliers. But if you do know the mean and the standard deviation, you can add 2 standard deviations and subtract 2 standard deviations to get your fences that way as well. So that's a very, very common question. I mean, it's come up multiple times in the last couple of years on that first FRQ dealing with exploring data. Hey, talk to me about outliers. Describe how you're going to find outliers, and then actually do it to check if you have any outliers. So do that as well. Why is mode a better measure of central tendency in a skewed distribution? It should be the median, not mode. I don't know if you meant that, but the AP curriculum teaches that when you are skewed, median is better. And the reason why that is is because when you're skewed to the right, for example, the mean gets pulled to the right because of those outliers and skewness to the right. So because the mean's getting pulled, it might not be truly reflective of the center of the data. And if you're extremely skewed to the right, the median is going to be a way better reflection of the center of the data because it's going to be kind of ignoring those extremely high values at the pure top. So hopefully that answered that question. What is the difference between completely randomized design, block design, and matched pair design? Can you specify any keywords to identify which one's which? Yeah, for sure. So completely randomized design, you got 100 subjects, 50 get treatment A, 50 get treatment B, done. If there are differences between the subjects, which anytime you're working with human beings, there's going to be differences. We just hope that they are evenly sprinkled among, boys, girls, young people, old people, people with good diets, bad diets, exercise. They're sprinkled into both groups through a completely randomized design. Now, randomized block design is that the problem specifically says, hey, we think diet matters to the response. Diet will definitely affect the response. We don't want it to. So what we're going to do is we're going to create a block of people on good diets, a block of people on bad diets, a block of people on medium diets or just average diets. Then in each block, we're going to randomly assign subjects. So maybe there's 20 people in the bad diet group, 10 randomly get A, 10 randomly get B. Maybe there's 30 people in the good diet group, 15 get A, 15 get treatment B. And then maybe there's 40 people in the average diet group, 20 get treatment 1, 20 get treatment 2. Now, at the end of the day, we still have 2 treatments, 1 and 2, A and B, whatever you want to call them. But now through blocking, we've guaranteed that in treatment 1, we got good diets, average diets, and bad diets. In treatment 2, we got good diets, bad diets, and average diets. Therefore, our 2 groups are very, very, very similar. And when I say similar, I mean that they're very different inside. So this group that's doing treatment 1 is very, very different inside. It's got all different diets, and same with this other group. That's going to handle confounding variables because now you can't say, well, that treatment group worked better because they all had good diets. It was the diet that made them better. No, in that group, there were good diets, bad diets, and average diets. It had nothing to do with diet because there were good diets, bad diets, and average diets in both groups. So when you see that there's a variable that we blocked on first, that's going to be that block design. Matched pair design is what's very obvious that there were pairs of people put together because they were very, very common. Whether you're working with twins or something like that, people that were paired together. And then again, in each pair, one person gets the first treatment, one person gets the second treatment, and that must be decided. Okay, I'm losing my voice here. Okay, couple more questions and I got to go. Is there a lot on empirical rule? Honestly, no. You can memorize the empirical rule, but you have the TI-84 calculator that could get those probabilities for you. It's like, what's the probability that you have a z-score greater than 1 in a normal distribution? Okay, if you know it, then if you know the empirical rule, then you should maybe know that off the top of your head. But again, grab your calculator, do a normal CDF from 1 to 99, and you're going to get that probability. So there's really no need to remember the empirical rule or use it. So hopefully that makes sense. Okay. Please talk about hypothesis testing and how to know which to use. Okay, so how to know which to use. Read the question. 4 things. First, does it deal with proportions? Does it deal with means? If it deals with proportions, you're going to do a z-test. Or if it deals with means, you're going to do a t-test. Then, is there 1 sample or are there 2 samples? If there's 1 sample, then you're going to do a 1 sample z-test for a population proportion or 1 sample t-test for a population mean. And again, go to that formula sheet because everything you need is on that row there for proportions or means 1 sample. Now, what do I mean by 1 sample? Well, I mean, literally, the problem said there was just 1 sample that we measured it. Or are we looking specifically at the difference between 2? And again, read the problem. I mean, it will say, hey, we're looking at the difference between boys and girls. 2 samples, 1 for boys, 1 for girls. We're looking at the difference between green bullfrogs and yellow bullfrogs. I keep bringing up bullfrogs. Well, there's clearly 2 different samples, 1 from each. So again, that's when we're going to be looking at 2 samples and we care about the difference. Now, don't forget about that special matched paired t-test. That's when we looks like we have 2 sets of data, but we really only have 1 sample that got measured twice. If you got 1 sample that was measured twice, it's that special t-test where we only care about the differences between those 2 match pair data. If it's chi-squared, okay, then you're talking about categorical data. If you have categorical data in a two-way table or in some type of table where it shows different categories, blonde hair, brown hair, green hair, pink hair, blue hair, whatever, right? That's clearly going to be a chi-squared test. Goodness to fit test, if there's one categorical variable, if you see a two-way table with two categorical variables, then it's going to be a chi-squared test for homogeneity or independence. So hopefully that was a quick answer to that question. It might not have been extremely detailed, but hopefully that was enough. There's no specific rule for how to round decimals, somebody asked. I always tell students, I like to go significant digits, to be honest. I always tell students 3 significant digits. It's kind of my thinking. Why can't you use the 10% rule for an experiment? It's because you're not sampling from the population. Now, if the problem said we had 100 people randomly selected from the population, then 50 of them were randomly assigned to treatment 1 and 50 of them were randomly assigned to treatment 2. Well, because you had that random sample from the population, then you would need to check the 10% condition. But if we just had 100 volunteers, which oftentimes when you're doing an experiment, you have to use volunteers, then you have the random assignment, 50 got A, 50 got B. Okay, you need to check that random assignment because that first condition is going to be random, but you don't have to check the 10% condition because we weren't sampling from a population. That's why. How to interpret variance. I wish I could say don't worry about it, but really, you're never going to be asked to interpret variance. You might be asked to interpret standard deviation, how far typical data is from the mean. That's the interpretation for standard deviation. You really shouldn't have to interpret variance. When can you generalize versus causation? Oh, great question. Okay, so in an experiment, if you want to say X causes Y, you have to have random assignment. It has to be very clear that you had subjects and who got what treatment was random. If you don't have random assignment, you cannot use the word cause. Awesome. Now, when can you take that information and generalize it to the population if the people in your experiment were randomly selected from the population? So if the people in your experiment were first randomly selected from the population and then randomly assigned to the treatments, you could say that there's a cause and effect relationship, and you could infer that relationship to the greater population from which that sample came from. But if you were using volunteers, okay, but you still had random assignment, 100 volunteers, 50 got A, 50 got B, you could use the word cause. You could say that X causes Y, but you could only say that that's true for people similar to the volunteers. So you would not be able to generalize that data to the greater population, only to people that are similar to the volunteers in your study. So hopefully that makes sense. Does the 10% rule apply for any type of significance test or just one sample? No, it applies for any, even if you're doing a 2-sample test, if each sample came from a random, if each sample was selected randomly from a population, then you got to check the 10% condition. So if you guys say, I took a random sample of 50 boys from the population of boys, and I took a random sample of 50 girls from the sample of girls, or from the population of girls, well, then because you were randomly sampling from the population, you got to check that 10% condition. Just wanted to thank you before you leave on behalf of everyone here and all your answers. Thank you very much. Appreciate it. I didn't mean to click on that, by the way, but self pat on my back. Thank you very much. Pooling, please, then I'll shut up. Okay, so the only time you have to pool, and if you're like, I don't even know what he's talking about, then honestly, don't worry about it. But because it'll take too long for me to explain. But if the only time you have to pool is a 2-sample z-test for the difference between population proportions. That's the only time. And the idea is that the null hypothesis is that your 2 population proportions are equal. So why do we even have 2 different together? Just put them all together. Like, why do we even have a sample for boys and a sample for girls? If boys and girls are all the same, why don't we just put them all together? And that's the whole idea of pooling. Now, you only use that p hat pooled to create your standard error. But here's the thing. If you were forget to pool and you don't pool your proportions together, you treat them separate. You use the standard error non-pooled. If you do everything else correct, you're still going to get full credit. You'll still get that E for essentially correct, because the difference between standard error unpooled and standard error pooled are like minuscule. So it shouldn't be a problem at all. But 2 sample t-test for the difference between population means, don't pool. Don't need to pool. Okay. Do you use p hat c for the large counts condition and a difference of 2 proportions? Yes. Yes, yes, yes. Technically, you should use that p hat combined or p hat pooled, however you want to word it, for the large counts condition for a difference in 2 proportions. Yes. Now, let me be honest with you. If you were to forget that and you looked at each sample separately and said, hey, in this sample I got 10 or more successes, in this sample I got 10 more successes, trust me, you probably will be fine. Like, I'm not trying to, tell you the wrong thing here, and college boards will say, oh, he's telling me the wrong thing. I'm just saying, like, if you do all that work, you got your hypotheses correct, you got the z-score correct, you got the p-value correct, you nailed your conclusion, they're not going to like take off 100 points just because you used the wrong p hat to get that large counts condition met. Well, how do you study for probabilities? Yeah, probabilities is for a lot of kids very difficult. I always tell kids, like, keep it simple. Know the formulas for probabilities. So I'm actually going to bring that up real quick here. Here we go. So right here we have the probability distributions. This first one is the probability for A or B. It is the probability of A plus the probability of B minus the probability of A and B. Anytime you read a problem and there's 2 things going on. Oh, the probability that this breaks. The probability that you read a problem, there's 2 things, A and B, 2 different things. And it talks about A or B and A and B. You're probably going to use that formula. Like, it's pretty simple. Then we have conditional probabilities. Anytime you're having a probability which says, hey, what's the probability of this on the condition, or given that this occurred, you're going to need that probability, this conditional formula. The numerator is the probability of A and B, and the denominator is the probability of B. I got lots of good videos that talk about probability. So please, just honestly, I don't have time right now to go over all these different examples, but go into my YouTube channel, and under the little magnifying glass, little search box, type in probability. You'll probably get tons of videos that can walk you through all different types of problems dealing with probability. All right. How do you create a discrete random variable distribution? Okay, great question. So you either are given one, which is like best case scenario, right? Let me pull up a little blank piece here. If you're given a probability distribution, that's awesome. You could kind of just, you have it there. You don't have to do anything to create it. Hold on a minute here. Boy, I got like 3 different mouses here, so I'm using the wrong mouse. Okay, so if you are asked to create a probability distribution, you simply have to think about your outcomes. Like, what are my outcomes? For example, if we say, hey, there's a game here, and you play the game, and you could score 1, 3, or 5 points. You play a different game Y, and you could score 2, 4, or 6 points. And we say, okay, create a probability distribution for Z, the total points after you play game X and you play game Y, and you add them together. Okay, so this is where you just got to think. I think, okay, well, I could score a 1 on X and a 2 on Y. That would be a total score of 3 if that happened. I can do 3 and 2. That means I can get 5 points. I can get 5 and 2. I can get 7 points. You literally just have to think about the different outcomes that are possible. Now, if you think about how can I get 7 points, that's where you got to think, okay, well, there's a couple different ways. There's only one way I can get 3 points. I get 1 on X, and then I get 2 on Y. That's the only way. Now, 7 points, I get a 3 and then a 4, or I could get a 5 and then a 2, or I could get a 1 and then I can get a 6. You got to think about different outcomes. Now, once you list all of your outcomes, and this might be a terrible example, I'm sorry, but once you list all of your outcomes, then you got to find your probabilities, and that's where you got to read the directions. Maybe they'll give you a little probability distribution here. How do you get a probability of 1? Well, maybe that's 20%. How do you get a probability of 3? Maybe that's 30%. On Y, how do you get a probability of 1 or 2? Maybe that's 10%. Then you got to actually walk through and figure that out. So, okay, so to get 3 points, I need a 1 on X, that's 20%. I need a 2 on y. That's 10%. Multiply them together. There you go. There's your probability to get that. To get a 7, well, then I got to walk through. Okay, what's the probability to get a 3 on x and then a 4 on y? Multiply those together. That's one option. Or I can get a 5 on x, 2 on y, multiply those together to get that probability. Or I can get a 1 on x, 6 on y, multiply those together to get that probability, and then combine them all to figure out your total probability there. But in a lot of cases, the probability distribution for a discrete random variable is given to you. Okay, guys, I'm serious. Maybe one more question, and then I should have time here. Can you please go through some interpretations that we most likely encounter on the exam? Boy, interpreting slope for a least squares regression line is guaranteed to come up. Interpreting the coefficient of determination. That's the percentage of variation in the y variable that is explained by the variation in the x variable. That comes up from time to time. Interpreting a p-value is really important. It's the probability of an observed statistic occurring, or more extreme, on the assumption that the null hypothesis is true. Those are a lot of interpretations. Really, I mean, when you're talking about scatter plots, interpreting all that value is really important. S is the standard deviation of your residuals. And the interpretation there is, when you use the least squares regression line to make a prediction, it's what you're typically off by. So if I'm using a least squares regression line to predict the height of a soap suds based on the amount of detergent that I plug into the water, hey, I'm typically going to be off by 1.99 millimeters if that's your S value. So I know it's kind of a rough answer there, but there it is. So, all right, guys, that's it. That's all I got time for. I'm really, really sorry. I know there's lots of questions. There's hundreds of comments I didn't get to. I'm so sorry. I will try to get on. I'm a tennis coach in my high school as well. And tomorrow we have a big tennis tournament all day. So I will not be available tomorrow. But Monday or Tuesday morning, the day of the AP exam, I should be available in the morning as long as I can get my camera and everything up and working. So I should be on probably around 9 o'clock. I'll try to create a little live stream around 8:30 or 9 o'clock, and I can answer some questions there as well. But thank you guys very much for watching all of my videos. And listen, I'm serious. If I didn't answer something, I guarantee I have a video that covers it. All you got to do is go to my YouTube channel and search, because sometimes you go to my YouTube channel, you only see what's most recent. But I got videos that are 10 years old that might explain something to you really, really simply and really, really helpful. So please check out my YouTube channel. It's got so much more. If you're interested in more practice, you got the Ultimate Review Packet at ultimatereviewpacket.com for AP statistics. So anyway, love you guys. Thank you so much for participating tonight. And hopefully I benefited some of you a little bit. But, closing words here, honestly, have confidence. Understand that you might get a lot of questions wrong, but you could still get a passing score of a 3. I mean, typically in most years, around a 60 to a 65% on the exam is a 5. I mean, that's a D, and you're going to get a perfect score of a 5. So have some confidence, work your best, answer every single multiple choice question, really try to eliminate answers that you know are wrong and make a good guess if you don't know. And on those FRQs, always write in context. Write, and do everything you can to get 1, 2, 3, 4, and 5 completely finished. Even if you're not confident, put something on paper. And then for number 6, just do your best. Read part A. Part A is usually really, really easy. I bet most of you guys can get part A correct, and then you might get 1 or point or something like that there. So, all right, that's it. Love you guys. Talk to you later.